Okay. So one of the really interesting things about water is that it can become an equilibrium between phases. And so you can have a gas phase floating in the atmosphere, and you have a liquid phase here. And if those are in equilibrium, then there's an energetic relationship. And so that means that if I pull the liquid water under negative pressure, that means it actually becomes more energetically favorable for water to go from the atmosphere to the liquid phase. So it dries out the atmosphere. And so we actually see there's a relationship between the humidity of the air and the tension, the pressure of the water. And that would be called the psychrometric equation. And the psychrometric equation says that the pressure, and this is going to be the water pressure, the liquid water pressure, is going to be equal to R bar T times the logarithm of the relative humidity. This is the temperature in degrees Kelvin, and this is the specific gas constant, which is equal to the universal gas constant divided by V bar, which is the volume of liquid per mole of that. So in the case of water, that would be 18 milliliters per mole, okay? Approximately, okay. So here's the psychrometric equation, which is a really interesting thing, that basically the relative humidity of that, so we have this curved water surface, so this would be liquid, and this is vapor. So the pressure in this liquid is related to the humidity, the relative humidity of that air there. Okay? So these two things are linked. Now, what's interesting to look at are some values of those numbers. So, for example, at a pressure equal to the permanent wilting point, this is when plants die. That's often taken as minus 15 bars. So minus 15 bars. The relative, so that's our pressure. And the relative humidity is, drum roll please, 99%. So in other words, by putting water at a negative pressure, it does reduce the humidity, but not by much. So in fact, if we went to minus 100 bars of pressure, which by the way is 1,000 meters of water column, then the relative humidity is equal to 93%. So, and frankly, it's very, very, very hard to get soil even to minus 15 bars. So what do we learn here? We learn that generally speaking, soils have gas phase that's nearly 100% relative humidity if there's any water. This is a very, very important point, that in a soil that has any little bit of water left, the humidity in that soil is essentially 100%. And only when the soil becomes absolutely dry does the humidity drop from that 100% value. So this is the relationship between pressure and relative humidity that we see really has some important implications about the fact that the gas phase in the soils are typically really, really moist.